Welcome back. Today we're going to talk about 3 reasons why your evaporator coil is freezing up. I hope this video helps you out. Stay tuned. In today's video, we're going to talk about 3 reasons why my evaporator coil is freezing up. I'm just going to go over this. I wrote this down. We're going to erase this as soon as I'm done so I can give you some illustrations. There's a lot of reasons why an evaporator coil can freeze up, so I don't want anybody to think that there's only 3, but there's 3 main reasons, and we're going to try to get through this. And the better you understand superheat, the more you're going to understand these 3 reasons. And as I walk you through this journey, my goal is to make sure that you fully understand that, so you're utilizing your gauges properly. When you're inspecting air conditioning systems, high temp, you're looking for the proper superheat range, so you're navigating through your problem, your diagnostic, and finding out which one of these 3 reasons could be the reasons why your evaporator coil is freezing up, or to make sure your system is just generally working properly. The first reason that I have up here, not enough heat being absorbed through the fin plates, so a dirty coil. When you're inspecting your system and you're checking your superheat value, a low superheat will identify this. It'll point you in that direction. 2, not enough airflow, which will reduce the heat exchange. Clogged air filter, duct issues, blower motor not moving enough CFMs, anything related to the coil being flooded out with too much liquid refrigerant. And again, a low superheat will identify this issue. And then 3, not enough refrigerant moving through the coil to keep the saturation temperature above a freezing point. Everybody knows water freezes between that 28 and 32 degrees, so you got to keep that saturation temperature above that. Either the system needs more refrigerant, or the refrigerant flow is reduced or restricted. The coil may be not matched properly with the condenser unit. Maybe you have a 36,000 BTU condenser and a 20,000 or 24,000 BTU evaporator coil. You know, that would be not matched. The coil may not be matched properly with the condenser unit. The metering device may be too small. It could be failed, or the pre-screen could be clogged. A high superheat will identify this. I'm going to go ahead and erase this, and then we're going to get into illustrations to help you better understand this. So just go ahead and I'm going to give you a second so you can just kind of go through this again. Okay, that should be good. I'm going to go ahead and erase all this. Okay. All right. We need to understand coil technology. All right. So I'm going to hold up an evaporator coil. Not that you haven't seen one or don't know what one looks like. This is an evaporator coil. Okay. This coil has got the tubes that run through it. It's got the unions that take the tubes and allow the refrigerant to flow through it like a coil is supposed to be. The fin plates. There's so many of them on there, so you get the right heat exchange. We have our TXV valve. You can see that we've got our small capillary tubes coming out of the expansion valve side that are feeding liquid to our coil. And then as we boil that liquid refrigerant off, we're coming back through our larger lines, and that's moving through that process tube. And you're checking your superheat outside. You're not checking it at the air handler. Your most accurate way to check your superheat would actually be leaving the evaporator coil before it goes anywhere else, because you can change by a degree or 2 or more after you leave the coil. In another video, we're going to go over that. First, I want to make sure that you fully understand, at the coil, what we should be getting, and then other things that just don't make sense, what could be contributing to that. So I'm going to pretty much just go over this coil technology with you. I'm not holding up an A coil because that'd be a lot heavier and harder to do this video with. but the coil that I have up here that I'm going to build my coil, it's an A coil. Okay, first let's just kind of look at a couple of simple things. You got to take a piece of sheet metal, right? And if we were to take this and to say we want to cut strips of this out and we're going to assemble this coil, it's got to have holes in it, and then we're going to run copper tubing through there, and by the time we're done, this sheet of sheet metal will be looking like Swiss cheese, and each strip would be about 2.5 to 3 inches wide and roughly about 25 to 30 inches long. Give me a second while I go off screen so I can kind of show you what I'm talking about with a section of a coil that I have in our classroom. And so if we were to just cut a section of coil out, this is approximately about 1 inch, maybe 1.5 inches. You can see how the tubes just pass through there, right? And then so if we were to count how many of these plates are here, if we said like within 1 inch, you know, how many, if we were to just take our tape measure and say, how many of these fins are within 1 inch? It's pretty simple. We're going to get about roughly 12 to 14 fins. And so we're going to do a little bit of math here so you can understand. I'm going to hold this other coil up here again. If we were to take a measurement of how long the fin plate is, how wide or depth of the fin plate itself, how many there are. They're both double-sided, so you have, you know, 2 sides of a fin, right? You have the back side and the front side. How many of them are here? And then we're going to get into the tubes. You know, how much tubing is in here. And we're just going to really break this coil down so we can better understand and respect, you know, what we're trying to achieve here when we're talking about proper superheat levels. If I said that just this represents one fin plate, it has no holes in it, right? But we can simply say that this plate is roughly, we're going to say this is 2 inches between here and here. And we're going to say we're roughly 25 inches long ways. This is before we drill any holes out. Okay. And so if we just did the math on that, use my calculator on my phone, we have 25 times 2. That comes up to 50 square inches. All right. Now, 50 square inches will eventually be converted to square feet here very shortly. That's times 2 because this plate is 2 sides. So really, it's 100 square inches. So we have 100 square inches. So 100 square inches. Now, most coils are about 20 inches deep, right? And if we were to take, you know, the amount of fins that there are within that 20 inches, if each 1 inch represented 12 fins, okay, and we had 20 inches in depth, then we would just take 12, we would multiply that by 20, and we would come up with 240 fins. And now we need to multiply that by 100 square inches. So we're going to go ahead and do that. And we get 24,000. That's square inches. So I want you to now look at this and convert this to feet so we can make a little bit more sense. We're just going to simply divide by 12 because there's 12 inches in a foot. and that comes to 2,000. So now we're going to say there's 2,000 square feet, right? And that's just on one side of a coil. So if we had an A coil, we would just simply just multiply that by 2. We come up to 4,000. And then there are some coils that are even 6,000 square feet. And what we're talking about surface area. And so we're just going to leave that up there for a second. I'm going to go ahead and write this down here. 2,000 square feet times 2, because there's 2 coils. That would represent an A coil. Times 2, which is 4,000 square feet. So you got to think about that. If you had a 4,000 square foot home and your job was to clean the surface area that you're walking on, you're not going to clean that by just passing a wand over it with a little bit of water and just say, hey, it's going to self-rinse. And if you did, you're only cleaning so much. You're depending on that chemical to break down the dirt, to dissolve it, to rinse it down with the humidity that's collecting on the coil, or maybe you're putting some water behind it to help rinse it off, depending on what mode you're in, what area of the US you're in. If there's a lot of humidity, they can self-rinse. But at the end of the day, there's only so much you can do with this. And when you're actually cleaning these fins with just a brush, you're not touching the fin plate, you're touching the very edges of that plate. You're touching the very edges of the plate here, right? And so that's not really cleaning anything. You're just removing some debris that are on the very edge of that plate. When we're talking about cleaning a coil, we're talking about, corner to corner here. If you mapped it out, it's 4,000 square feet minimum to 6,000 square feet. It would take you a very long time to actually clean that right. Now, it comes brand new and clean. And so the idea is to keep it in that condition, utilizing proper chemicals and proper maintenance. But a lot of TLC has to go into this to make sure that things are good. Because what's happening here on this fin plate is if you get the right amount of airflow going across this fin plate, then this fin plate will absorb that heat because this plate is cold. And so we want to make sure that every part of this plate is gathering as much and absorbing as much heat as possible so it can be transferred onto the tubing and out of the tubing into the refrigerant, boiling that refrigerant off, that state change, and then that heat is transferred outside and then rejected, and it's coming back as a cooler refrigerant in a liquid state, and then the process just continues to repeat itself. And that's when the system is mechanically working properly, and then we don't have to worry about any interruptions in that refrigerant cycle of a breakdown or something of that nature that's mechanical related due to neglect. So just the fin plate itself is, you really have to understand how much surface area there actually is, and it's in a confined spot. And so it's very important to have all those 3 things that we talked about. Ducking has to be right. The CFMs have to be have to be at the right matched air rate, RPMs, and flow going through the coil so we can get that heat exchange. The coils have to be clean. There can't be any additional pressure drops that aren't as part of the design, so there's no interruptions from refrigerant flow going through those tubes. And the process is just that simple. Taking this a step further, I'm going to go ahead and just now that we know this math, let's go ahead and erase this. So now you know how we get to 2,000 square feet on one coil, or 3,000 square feet on one coil, A coil being twice that. Go ahead and shrink this down. We'll go ahead and move this image over. And as we continue that journey, the very next thing that we would be looking at doing is, all those holes that are on the fin plates, so the copper tubing can pass through. You're not losing surface area, because you still have the amount of space between this plate and the next plate that has, this surface area that's been removed on the tube. So it's the same surface area all the way through. And so the debris starts to collect between these holes as the tubing starts to go through there, and that just further derates the heat exchange, because now you have a reduction in airflow, plus the plate is dirty, so now there's less heat being absorbed on top of that. So the problem just gets larger and larger. Let's go ahead and continue on our coil technology. We're going to go ahead and go to our next image. These plates are obviously stacked up as we just went through. When we start looking at how many plates there are, all the tubes that are passing through there, we get to a number of plates, and it's just impossible to get in there and clean these. That's why a pull and clean is extremely important. Once a coil gets to a certain point to where it can no longer be maintained in its present state, it has to be pumped down, coil cut loose, taken outside, and pretty much cleaned, utilizing garden hoses and chemicals and all that stuff that we can't do inside the home because it's going to make a big mess. You can't take a garden hose inside the house and do an acid wash. That's just not going to work out. Okay, we're going to go ahead and continue. Let's go ahead and talk about the tubes. If we look at the tubes themselves, just the copper tubing, now this is pretty interesting. If you were to measure the tubes, just one tube from front to back, if we're saying that we're basically 20 inches, do a little bit more math here, if we're basically 20 inches this way, right, and say there's like an A coil would probably have 72 total tubes, then we can say 72 times 20 inches, get my calculator back out, that would be 1,440, yep, 1,440 inches. And of course we want to just go ahead and divide that by 12 inches so we can get a foot, and we'll say that's 120 feet. So one slant coil could be 120 feet of just copper tubing or aluminum tubing passing through those fins when we count them all up. Next time you're on a maintenance or you're working on one, count how many tubes you have, do the math. It's crazy. Now A coil, you're easily going to be double that. So we're going to come up to about 240 plus feet of copper tubing. Now, if you think about a roll of coppers, 3/8 copper tubing, just that liquid line by itself, it's about 50 feet. And you think that's long. That's crazy to think that there's about 5 times that much just in the lower half of that air handler, going back and forth, back and forth, back and forth. Okay, that's quite a bit. That's quite a bit. And when you start having a respect for this, you start understanding that things have just got to add up. They have to make sense. They have to match. It's so critical. It's so important. All right, I'm going to go ahead and go to that next image. How that refrigerant flows through that coil is pretty simple. I think everybody pretty much has an understanding of that. Very simply, your tubes, as they go through there, this one's going to come through here, it's going to come back, and that's pretty much it. That's really all that's going on here. Nothing really special there. So you all have an inlet and an outlet. And I want you to think about this for a second. Your entire coil, as I've said in other videos, doesn't have one in and one out. There are many inlets and many outlets, which means your coil is broken into many sections. I'm going to go ahead and hold this coil back up so we can look at that. So after we leave our expansion valve, we have these capillary tubes that are your inlets to sections of the evaporator coil. And we can count them. We have 1, 2, 3, 4. There's 5 here. And how many am I coming out with? 1, 2, 3, 4, 5. Right? And so there are 5 sections to this coil. And so this design, this image would represent one section, just one section. So you can have 1 or 2 sections of your coil that are dirty, where the thin plates are not absorbing heat, where maybe a lot of debris is also collected on these tubing, and air's not circulating very well through that, so it's not getting enough heat onto the coil, and a little bit of heat that is getting on the coil is not being absorbed onto those dirty thin plates. Okay, and you may have 1 or 2 of those sections like that, where the majority of the sections have been better maintained and are doing pretty good. We'll go ahead and reduce the size of this image, put it back over here. All right. We have our expansion valve, metering device here. Okay, the metering device, this is the only pressure drop. So on one side, I'm going to have a high side. Go ahead and write that down. Will be a high pressure over here. Will be a low. I'm going to go ahead and just do this side in blue. This will be a low pressure. Okay. Over here, this is liquid. Okay, that's a state of the refrigerant that's in a liquid state. We are also in a liquid state on the other side of the valve. And so this is a critical point, because we have to have the proper pressure drop, and it has to meter the right amount of liquid going through this valve. So all those capillary tubes, whether there's 5, 6, 8, 10, or 12, however many are there, all of those are getting the right amount of refrigerant flow. So there's no interruptions there. Okay. There's a power head that has actually got its own gas in it, and then that sensing bulb is actually heating up based on the temperature of the return line. And I'll point that back out with this coil here. As you can see, the sensing bulb here is not connected. If it were connected, it would pretty much be, connected right in this area here. My hand's kind of in the way. And, so we're actually taking the sum of all 5 of these sections of coils, right? So I can have different numbers here, low numbers and high numbers. I can have liquid coming back on some of these. I can have vapor coming back on others. So I have low superheats and proper superheats. And the sum of all that is going to give me a temperature reading here, which is going to expand the gas that's in this tube, and it's going to allow this valve to open or close based on that temperature, based on the expansion. And so if I don't have proper flow of refrigerant because of something here, or maybe a pre-screen is clogged or something, or maybe something that's not sized properly here, then that's going to cause issues with superheats. And if I don't have the right temperature on that coil, it's going to grow ice. We'll go ahead and erase this image. I'm sorry, not erase the image. We'll go ahead and erase the writing. Reduce the size of the image. Go ahead and get that out of here. All right. Let's talk about that airflow for a little bit here. All right, in this image here, we have the more CFMs, the higher the superheat. I want you to start looking at the blower assembly, the blower wheel and the blower motor. You have air coming in on the sides. It comes out, gets through the ductwork, and your forced air is now going through the whole house, right? Well, stop looking at that and just as in a motor and a wheel, and start trying to compare that to the speed of this, and the amount of airflow that is moving through that cabinet is pretty much compared to what I like to compare it to is like a flame, right? And so am I cooking with low heat? Am I cooking with medium heat? Am I cooking with high heat? And so if I'm trying to boil a vapor off, if I was trying to boil off water, I wouldn't do it on low. I'd do it on high. If I was trying to boil water and I'm boiling a pot, I need to hit 212 degrees to hit that. Well, I mean, we're talking negative 50s in Fahrenheit on our boiling point on refrigerant. So, I mean, there's plenty of heat in the air if that is our boiling point in the negative 50s, right? And so, we don't need 212 degrees of heat, but you have to think about the refrigerant flow that's moving through the coil, and how everything is compressed in 240 feet of tubing, and 6,000 or 4,000 to 6,000 square feet of fin plates, and you got to have the right amount of CFMs. It can't be too much. It can't be not enough. Especially if it's not enough, you're not going to have enough superheat, and you're just going to flood that coil out. But if you compare this to a flame, you'll better understand that the more air that I have, then also the more heat I'm going to have. And I'm not saying that you should put these things on high speed, but I'm suggesting that if you had poor ducking and you're going through motor issues, I guarantee you have low superheat issues, and your coil's been freezing up, and it's not just related to one or two problems. It's probably related to a number of problems, but it boils down to one simple thing: you don't have enough heat getting on that coil. So you want to make sure you're getting the right amount of heat on that coil, so we can boil that off and not return back in a liquid state. So I'm comparing this blower section to, the more airflow we have, the more heat we're going to have. In the absence of the proper amount of CFMs, you're not going to have enough heat on that coil, and then the rate of refrigerant flowing through there, it's just not going to be enough to boil that refrigerant off to a vapor, and you'll have a low superheat and return most likely in a liquid state and kill that compressor. All right, we're going to go ahead and reduce the size of this image. All right, and so as we went over these sections of coils, there's tons of them, right? This would represent a return line, right? And so if I was coming in to, I'm just going to draw you a quick little put my expansion valve back over here too. If my expansion valve was feeding one capillary tube into here, right, then my return line would be coming back on one of these. So so that's just one section. I would have to have another one of these for another capillary tube, and then out of that back to here. And so as we start to build this, we're going to understand that our coil is in many sections, as I've said in the other videos, and we need to break down, the fact that if we have a 5-ton, a 4-ton, 3.5-ton, whatever the ton, it doesn't matter what it is. It could be on a much larger scale than that, 10 tons, 15 tons, 30 tons. That doesn't matter. You have to look at that coil and respect it, that if you see dirt on it, if you see something that's not right with it, then there's something that needs to be done to it. And that's what you're there for, is to give it your best and to make sure that you're leaving that system in better condition. There's no reason for you to walk up to a system, whether you're maintaining it or working on it, and not leave it in a better condition, or at least quote it to be done in a better condition. If something extensive needs to be done that you just can't do while you're there for free. So I'm going to go ahead and just bring my cup analogy into this, and we're going to just try to quickly go through the superheats again with the sections of the coil. I'm going to go ahead and just erase these lines here. I'm going to reduce the size of this image and drag it back over onto my tool section. Okay, we'll take our evaporator coil that I've designed here. It's a little bit different than what you're used to. Looks kind of funny. And we'll say that, you know, I can put my expansion valve in here, I believe. Nope, it's not going to let me. We'll put my expansion valve over. We'll leave my expansion valve right here for now. Let's see here, and we'll see how close we can get this image. I don't think it's going to let me. No, it's not going to let me put that image too close to it. So what we'll do is we'll just draw some lines on it. We'll put this over here. That should work out. Okay. All right. So I know my expansion valve is not as big as I'd like to make it. I'm just going to try to bring it down here where, see if that'll work. Okay, good. All right, so in this we see, let me move these out of the way too. We see our process tube that is carrying the refrigerant back to the suction line so it can make its way out to the compressor. This is everything on the indoor unit. I have 1, 2, 3, 4, 5, 6, 7, 8. So this would represent 8 sections of my evaporator coil. We're going to come in with our liquid line. It's going to come in to our expansion valve. We're going to have our pressure drop. We're going to come out of that, and we're going to start to feed different sections of our evaporator coil. Starting to look like a coil now. And what we're doing is we're feeding these sections liquid, and at the rate of our heat exchange, given that there's enough refrigerant in the system, enough airflow, and some very clean fins so we can absorb heat, we're going to boil this liquid refrigerant off, and then we are going to return back to the compressor through this process tube that's right alongside your evaporator coil, okay, in a state of vapor. I'm going to go ahead and draw some line. I'm going to go ahead and pick a different color blue. Should something a little bit darker there. Okay, and we're going to just draw these over to these cups, just coming across so you can get a good clear image on what we're talking about here. So we had these small lines were our inlet tubes. The larger lines are the outlet tubes. Oops. There we go. And so we have in, out. And so we could get a superheat reading on every single one of these. There's 8 of them here because I have 8 sections. So I have 8 capillary tubes. I have 8 return lines coming back to my process tube, which is my suction line going back. And so every single one of those sections, you do blow this up a little bit. Basically, every one of these sections represents what you're used to seeing in a textbook. Okay, so one's an inlet, one's an outlet. All right, so we'll go ahead and just rotate that around. Right, and so we have an in and an out, an in and an out. So 1, 2, 3, 4, 5, 6, 7, and there's 8 of these. All right, and so we have to make sure, however many sections there are, we have to make sure all of them are boiling off that liquid refrigerant that's entering that. Okay, and so we're going to throw some numbers up here, and we're going to look at these cups, as some of them may be full, some of them may be at the proper level, the proper ratio, some may be empty, and that's going to govern a high superheat or low superheat per section. And then the sum of all of them would give us a total reading going back. Hopefully that number does not change as that goes from the indoor unit to the outdoor unit, as it has to journey through a chase, the ground somehow if it's not insulated, or a hot attic crawl space that can be flooded out, muddy, whatever. Anything that is going to change the temperature of that refrigerant from this point to the point outside will throw your reading off, and if you're not careful, you could make a poor decision there. So we will have a video on that, so you can make sure that if you have been in that situation, you better understand why. But right here, every one of these, ideally, if we're looking for 12 to 18, if we're looking for 12 to 18 degrees superheat range, then a perfect world would be like I got 16 degrees here. They're not all going to be the same temperature, so I'm just going to write anything that's between 12 and 18. We're just going to keep writing values here. We'll say that this one is 17 and this one's 18. And now, so that means that every one of these has a really good superheat. This would be like something that's just absolutely running in tip-top shape. So let's just see what that would look like. We're going to go 16 plus 15 plus 14 plus 12 plus 18 plus 16 plus 17 plus 18. I just went all the way down. And that comes up to 126. So the total of all these is 126 degrees, but we're going to divide that by 8, and that will give it, that's the 8 sections, and that'll give us our average. So we're going to go ahead and divide that number, 126, divided by 8 sections. So our superheat would be 15.75. We're going to go ahead and round it up. So we're going to go ahead and say 16 degrees. So when you're outside, you're actually reading 16 degrees superheat, at your evap. Now, if you have a 16 degree superheat, that does not mean that, you're good to go on all this stuff. And that doesn't mean that because you have a 16 degree superheat that not only does it not mean that you're good on all these sections of coil, but it doesn't mean that your system's performing perfectly, right? You would have to really break it down a lot further. It just means that you're within a good range, and the compressor is not going to have any liquid returning to it. That's all that really means. But it does say something about the performance. But let's just say, let's do another scenario here. I'm going to give you different temperatures. Let's just say that this one was almost flooded out with liquid, and say it was performing at 0. and this one was kind of flooded out. It was performing at 2 degrees. So we're not doing very good already. But let's just say that the rest of these were doing a little bit better than that. So we had 12 here and 14 here, and say that we had 16 and 18, and say we had 22, and say we had like 24, right? Let's add those up, see where we're at. So we have 2 plus 12 that's 14, plus 14, plus 16, plus 18, plus 22, plus 24. That's 108. Divide that over 8 sections, right? We still divide it over that 0 because it's still one of the sections. That comes up to 13.5. So we'll go ahead and round that up, and we'll say 14. And so that means outside you're going to be running a 14-degree superheat. And so you might say, hey, that's within 12 to 18. It's good to go. I can't add any more. I'm not going to take any out. It's cooling fine. No complaints. But you can't sit here and say that this coil is just 2 factory specs, because I have 2 sections of my coil that are outside of this design. They were not designed to give me those low of superheat readings. But we're also not checking those sections of coil as far as what is my superheat leaving each of those sections. This is why it's very important to make sure you have adequate airflow. Make sure that your CFMs are proper on the blower. Make sure that the right horsepower in there and it's turning at the right RPMs. Make sure that there's no issues with high static pressure on your duct system. Make sure things aren't restricting there. Make sure that the coil isn't filthy. Make sure it's not plugged up. It could be a free draw. This could be in a closet interior of our home where maybe there's a piece of debris, like a piece of plastic or something, that just got sucked up. I've seen receipts get sucked up on these things, and plastic bags and all types of stuff. We've seen litter boxes underneath them where the cat goes in there and takes care of the business, and next thing you know, the coil, every time the cat's scratching a litter box, it's getting that on there. Well, that stuff on a wet coil turns into almost concrete, so it's pretty hardened. And a lot of that debris winds up making its way up to the very top. So it's in a lot of cases, you might have cleaner sections of coil here, dirtier sections of coil here, just over that. And then if the coil is being maintained, it's the hardest section to actually clean. I've seen technicians say the coil needs to be removed and cleaned, and I've seen other technicians come back and say, no, the coil is perfectly fine, because their visual observation was, no, it's good to go, you're fine. But that's also because they're not checking the coil, and they're not appreciating that the coil has this many sections. And if that top section is not good, then if you looked at that, if there's 8 sections here, right, then the percentage of this coil that's not working properly is pretty significant. And so the percentage on that is, each one of these is like 12.5%. And so your 25% of your coil is not even working right. So if this was a 4-ton, then I would say you're operating at 3-ton. And so, yeah, you may have a decent superheat over here, but that doesn't always mean that this system is working perfectly fine. If you had any other issues, if you lost just a little bit of refrigerant charge, if the coil got a little bit dirtier and these other superheat values started to drop, you're going to start to build up ice, because your saturation temperatures are much lower here, where ice will form. And once that ice starts to form, it's like cancer. It just spreads, and that sheet of ice will just grow. And a lot of cases, that's just what happens. And, things can easily be misdiagnosed because people think that, these things are built to handle that kind of abuse. But just because the machine's running doesn't mean that the machine is running properly. And just because you're getting decent pressures and decent temperatures doesn't still mean that you're getting 100% of its capacity. There's a lot that goes into this, which is what makes the trade fascinating. And if you home in on your technical skills and you look at it and you break it down this way, you're going to have less callbacks. You're going to have better results with your customer retention as well. I didn't want to take this video and stretch it out for a very long length of time. I wanted to just get a quick video in here where I've talked about other things and other videos kind of tied into here, talk about that coil technology, just breaking it down. So really this video is a part of a whole playlist of videos that we've been talking about with Superheat and Subcool. But if you're curious as to why my coil is freezing up, there are bigger things that you need to understand so you can accurately prevent that from happening. But refer back to those three things that I talked about, because that is a good process of elimination. And as long as you're checking Superheat and Subcool, it's going to help guide you on some of the quick things that you can start looking for, so you can start eliminating those things that may not be a problem and home in on what is a problem. As always, if you haven't subscribed, please subscribe to our channel. Like our channel, share this channel, push that share button, push it out to your buddies. Don't take this knowledge. My passion is extended to you through me teaching. And if you have a passion for this and you think that you can't well explain it, you can simply share this channel with others and say, hey, listen, this may help you out. Watch this. Leave me a comment. I'll read those comments. I try to get back to everybody. I work more than just in front of this big clear touch screen. This is just something we do to help continue educating our guys and technicians, and make sure that we're also sharing this knowledge with others, because it's one industry. It's not split up into whoever's way of doing it. There's a right way, and then there's just a wrong way. And I hate to put it that way, but you can either do this the right way, or you need to go back to the drawing board if you think that you figured out another way of doing it. There is no shortcuts here, and I believe that this industry suffers greatly from people not leveling up, not sharing knowledge, and I just hope that you're passionate about this, so we can make this industry better. So I want you to stay safe, level up, stay tuned. See you next time.